Okay, in the last class, we derived this formula. What is this formula? If you have a circular shaft, then you have a circular shaft, and shaft has a certain length. Then, if you apply the torque, and you are applying torque right over here clockwise, so over here it will react anti-clockwise. So T is the torque, and if R is the radius of the shaft, then this is the formula for the torque. Tau equal to TR by J. And you see, you put R value 0. That means you are at the center of the shaft. So at the center of the shaft, there will be no shear stress. Then R gradually increase. Then you are right over here. Then your shear stress will be maximum. And normally, not normally always, shear stress work parallel to the cross section. So if a parts fail by shear load, that means it becomes two part. And torsion, due to the torsion, we already proved that there always generate some shear stress inside the material. So this is the value of that shear stress. Now, in the material, we have sigma y, right? That means tensile yield strength. We have ultimate yield strength, the maximum stress you can apply, right? Then we have the rupture strength, R U T, okay? Rupture tensile strength. We are not worried these two. These two, if you loaded a structure until ultimate stress, then it will not come back from previous size, because yield strength is less than ultimate. Ultimate is the higher strength. Then you have sigma y. So always you stress the structure less than sigma yt. Now, what is the allowable shear stress of the material? Is not showing. So normally, half of the yield strength. Half of the yield strength is the allowable shear stress you can apply, or half of the ultimate strength, say sigma ut. So say ut is 60 ksi, for example, for a material. So what will be the ultimate shear strength, or tau ut? Tau ut will be half of this value, say 30 ksi, kilo pound per square inch. Now, shear stress of a structure made of same material, you calculate, you found 35 ksi. Then what will happen? It will break down or it will survive? Anyone?
Sir, can you repeat the question?
It will break down, material will break down, material will survive, that I'm saying. Say a material is given tau ut equal to 30 ksi. That much stress it can take. Now you have a shaft, the torque, say 2000 kilonewton or 2000 newton meter. You apply this torque, then you figure out the stress. Stress coming 35 ksi. My question is that your shaft will break down, or it
will break down.
It will break down. Good. Your ID?
135.
ID 135. Your name?
Azmine.
That means it will break. Okay. So either you need to increase the diameter, or you need to use higher material, right? And if you see failure mode of the structure by shear stress, I update on slide. It will like that. That when you see due to the torque, 1 second, excuse me. Okay, so due to shear stress, not shear stress, if you apply torque inside the material, it experiences shear stress and it becomes two part. This one for ductile material and this one for brittle material will feel like. Okay, so whenever you design a shaft or any other uh, object that carry torsional load, then we need to make sure that your structure is not failed. But in solid mechanics, we'll talk about only circular shaft, either solid or it might be hollow, but only talk with a circular. But in machine design, you will see you have a bar like C channel. This bar might experience torque. Say this side attached to something, and you apply torque. In that case, what will happen? Okay. For example, aircraft wing remain like this kind of shape. And way I sketch it seems like it's a very simple thing, but actually is not. There is some thickness of the skin. Might be 1 millimeter, depends on what is the thickness. Then it might be length, right? 20 feet or 500 feet or 300 feet, depends on what kind of aircraft. Then inside, they have a lot of material, like it might have some kind of eye-shaped beam to keep it all together. Say on over here, like that. So this, due to the wind, this structure also experience torque T. And due to the torque, it generates shear force. Then if you put a rivet over here or any fastener or nut bolt, you need to make sure the nut bolt is strong enough to carry the shear load. So, but this shape is not the circular. So by T tau equal to TR by J. T tau equal to TR by J. This formula you cannot apply over here. Even you can apply over here. So those two things. This is called closed channel. Torque under one is called open channel, right hand side, because cross section is open, is not close, right? But this one cross section is close. There is no opening. So we have two formula to figure out the torsional shear stress in those kind of structure. So just give you some idea that right now you are applying the torque formula, shear stress formula only on the circular shaft. So you might have question, what about the other type of structure? Okay, so this is our main formula, and this is the shear stress distribution we already discussed. Now we need to figure out the angular deformation. How we can figure out the angular deformation of the shaft. So if you look this formula, this figure, so right over theta is the angular deformation. That's theta value we need to figure out. And we already described this one, the gamma, this shear strain, this angle equal to r theta by L. Now, how we can figure out the value of theta? We need a formula. So value of theta, if you look carefully over here, this is our formula for the shear stress in the shaft. And this is our formula for shear strain, gamma equal to r theta by L. Now we know modulus of rigidity, G equal to tau by gamma. So at the top, TR by J, at the bottom R theta by L. That value is put in the right over here. Then if you simplify, value of R will be cancelled out. So you will have TL by J theta. So theta equal to TL by GJ. This is the formula for angular deformation. So we have two formula. Tau equal to TR by J and theta equal to TL by GJ. Now, you might have a shaft with multiple cross section, might made of different materials. So you might have a circular shaft, this much diameter, say made with aluminum. This shaft attached with this shaft, say made of steel, and this point is welded or joined fixedly, that there will be no slip between these 2 points. Then you have another shaft right over here. You might have another shaft right over here. So all the 4 shafts has different diameter, different size. Okay. So in that case, how you are able to figure out the value of theta? That means angular deformation. Or how we can figure out the tau in each shaft. Tau equal to TR by J. So how we can figure out value of tau 1 in this shaft, tau 2, and this shaft tau 3, and this shaft tau 4. How to figure out? Say you know the geometry of this shaft, length you know, this is L1, this is L2, say this is L3, this is L4. And if you know the diameter, you can figure out the result formula. Tau equal to TR by J. Now, if I say figure out the torque or figure out the shear stress in those beams, so you need the torque. Without value of torque, you cannot figure out the shear stress. J equal to pi by 32 d to the power 4. Easily you can figure out. R equal to d by 2. Easily figure out, right? So say length given, diameter given, so easily you can figure out the value of the G. So now, oh, I make a mistake. I delete everything. So this is, for example, one shaft. This is the one shaft. Other one is this shaft. And other one is this shaft. Okay. Now this shaft will figure out nothing is there, right? Now I'm saying you have like torque over here. There is a torque over here. There is a torque over here. So you see these 2 torque, this one and this one clockwise. So I'm saying this is 500 and this is 300. So 500 and 300 rotating clockwise. So obviously this one will be how much? All the summation of torque has to be 0 because this is solid body and we're working with the static body. So this one will be 800, right? 800 Newton meter or 800 feet power, depends on unit, right? Now, if I say this torque working right over here, the joint, this one in this joint and this one this joint. Length, diameter, you already know. Now, if I say that what will be stress in this structure, how will you figure out? You need to figure out the stress. So in that case, you need to know what is the torque in section 1. How will you figure out? So you need to make the free body, like axial load we did in the not this semester. You have been taking class with Shana sir, but this type of problem with the axial load we did in the lecture sheet might be 3-4 after you learn the stress strain. So what I'm like to say that I say this one we apply at the joint, but I don't know how much load over here. Okay, so you need to make a free body diagram like this shaft on shaft. This is the middle one, then bigger one, then the other one. Then we have to make the torque diagram, or you need to figure out what is the torque right over here. So if you know the torque in this shaft, for example, this shaft, this shaft, this shaft, then you can easily figure out the value of tau. For this shaft, tau 1, tau 2, tau 3, tau 4. But before that, you have to break the each member and make the free body. And we will show you later on that how we can figure out the torque for each segment by making the free body. But right over here, what I like to say that you know the torque at B is this much, ED this much, DC this much, and CA this much. How will you figure out the angular deformation that I'm saying? So angular deformation, if it is theta, then theta, you take this one, then it will be TB, that means torque at point B, or you can say B into LB divided by GZ, shaft B, moment of polar moment of inertia, plus then you have to take ED. This value ED, you'll get D LD plus GZD. If all are same material, you can use same Z. If material is different, then you can use the B over here, D. So then next one plus next one. That means you can say summation, algebraic summation of total deformation. Now, you look carefully, we derive the formula theta equal to TL by GZ. How we derive? If you look in this formula, which direction T is working? If you look from the right side, that means you are looking from 1 second. If you are looking from this side, then respective your eye, that means if you look from right side, then in that case, say this is I, this torque is rotating anticlockwise. And for this type of torque, we got theta equal to TL divided by GZ. So angle you find by this formula, that will be positive.
Sir, your mic is muted.
Oh, sorry. Okay, I'm not sure how much you miss it. But I'm saying that as per formula, we found theta equal to TL by GJ for this free body right over here. So in this formula, if you look from the right side, from this side, what is the T? This torque try to rotate this body anti-clockwise, right? That's why theta positive. And now if I give you a shaft, this shaft, I'm saying this end torque rotating anti-clockwise 200 Newton meter. And right over here, I'm giving you clockwise 200 Newton meter. So this will be, this torque will be negative or positive, that I'm saying. This torque will be positive because it matches with this orientation. If you look from right side, this T will try to rotate clockwise, and this one also try to rotate. I'm sorry, this is anti-clockwise, this is also anti-clockwise.
Anti-clockwise, yes.
Yeah, so in that case, if you found, say, theta 10 degree, so this 10 degree will be positive. That means torque is positive. But same shaft, I'm saying right over here, right for the working 500 Newton meter. So this is clockwise, right over here. It has to be anti-clockwise, right? So it has to be along this direction. Over here, 500 Newton meter. Now this torque, you'll consider is a positive or negative. That's what I'm saying.
Negatives.
Negative. Respect to this point. That I'm saying. So always you think the torque is positive, not negative, respect to this point. Okay. So you have a series of shafts. They have different material. They have different torque, different length. In that case, how will you find the average angular deformation? Then theta will be sum of TL by GJ. You will write down theta equal to T1 into L1 divided by J1 G1 plus next one T2 L2 J2 G2. If you have 5 parts, you have to add all the 5. This chapter is very simple. I put over here 3 problems. This 1, 2, 3, and I'll put one more problem and solve it. Okay. So if you look the first problem, what is saying, if a twisting moment of 1100 Newton meter impress upon 4.4 centimeter diameter shaft, what is the maximum shear stress developed? And also find angular deformation of the shaft. So at first you write down that what value is given. Torque T. So this is easy that you know this is our torque. You'll say torque in the shaft. It doesn't say that this is clockwise and anti-clockwise. The figure also not given. So you can make an assumption that torque is positive. T equal to 1100 Newton meter. And diameter of the shaft is given. So T, this is value of R, right? R equal to diameter divided by 2, the converted meter. What do you like to know? Maximum shear stress. That means they like to know what will be the tau, maximum tau. So where tau will be maximum? At the outer fiber and R at the outer point. And we say also find the angular deformation. So you know they want the tau, and also they like to know the value of theta. What is the theta? So we know that we have two formula, tau equal to TL divided by, tau equal to TR divided by J. So easily you can figure out. Is it T given 1100 Newton meter, R 4.4 centimeter, you convert in meter, then divided by 2. And what is the value of the J? Pi by 32 into D to the power 4. So diameter also given. So you'll get the tau. Although unit of tau, Newton per meter square, or PSI, or Pascal, right? Now, say figure out the angular deformation. So angular deformation theta formula equal to PL divided by GJ. So you see torque is given 1100 millimeter. G value right over here is given. L is not given, right? It don't say what is the length of the shaft. Now value of the G is given, right? Where it's saying 85. Value of the G on second, 85 gigapascal. Now you need to figure out the theta. Now only one problem you have, that length of the shaft is not given. Our formula theta equal to TL by GJ. For this length not given, how you figure out? G value we convert in Pascal, 10 to the 9 Newton per meter square. This one divided by 100, then divided by 2 to got the R. And J pi by 32 into D to the power 4. So diameter is given, you can figure easily. Now the value of L is not given. So how will you figure out? What we'll do, you see theta depend on L. If L increase, theta increase, L decrease, theta decrease. So this result, after calculation, you might get in terms of radian or you might get degree, right? Say after calculation, you got 100 radian, right? So in our problem, they like to know the value of theta, but no L is given. So you figure out the theta by L value. So theta by L value, in that case, you will get 100 degree or radian by per unit length. If length is meter, you can say 100 radian per meter or per centimeter or per inch. Okay. So this is the problem 1. I am not solving because this is easier. Now let's solve the problem 2.
Sir,
Okay. Yes.
Assalamu alaikum, sir.
Alaikum salam.
Sir, will you repeat the section again?
Which one? Problem 1.
Sir, yes, sir. Sir, how can we get L?
Well, L is not given, but they are telling you need to figure out the angular deformations. What is our formula?
Sir, Q is equal to TL by GJ.
L by GJ. But if length is given, is easy, right?
Yes, sir.
Say length I'm giving 2 meters, or what is the data? What will be your result? First you get radian, right? Say you get 1.15. That will be radian. Or if you convert in degree, just 1 degree. But right over here, L is not given. So you figure out this value, L by L. So L by L will be how much? T by G J. And what will be unit? You got, say you got number, you got 12. How will be unit then? Say 12 degree. So this will be 12 degree per meter. Your deformation will be, if you keep in radian, then you say this much radian per meter. That means its shaft length is 1 meter. Angular deformation will be 12. If shaft is 20 millimeter, then angular deformation will be this one into 20. You got it?
Yes, sir.
Okay. So this way you need to just solve it. Very easy. After you we solve problem 2, 3, then it will be easier for you. Problem 2. It's saying a hollow, that means inside is nothing, right? So it will be a hollow steel shaft, this kind of shaft. Mass transmitted torque. So value of T given over here. T equal to 25 kilonewton meter. The angle of twist is not to be exceed 2.5 degree. Angle of twist means value of
Theta.
theta. This theta should not be more than this degree. So theta equal to 2.5 degree. Then you convert in radian, right? You get a number. And right over here, you see you get one formula that theta equal to TL divided by GJ, right? And length of the shaft is given, L. Theta is given. So you get one clue from here. Value of G is given? No. G value is not given. But it's saying that theta should not be more than 2.5 degree. So this is your theta on data is given. Allowable shear stress is 90 megapascal. What is that one? Value of tau. That means this shaft,
Tau.
in this shaft, your shear stress should not be more than 90 megapascal. So you can say tau equal to 85 megapascal. Now it's saying figure out inside and outside diameter of the shaft or radius. Say this will be outside diameter D naught, and if you measure the inside one, this will be DI. That you need to solve. Okay. That we need to figure out the geometry of the shaft. What is the diameter of the shaft? So if I share a new screen, the math cat 5, let's see, I think I opened it already. Did you see the screen?
Yes, sir.
Yes, sir.
Okay. So you see, I can take it in the bottom, this one. Then you realize that how you can solve it line by line. Okay. So length is given 3 meter. Torque T 25. Angle of twist, that means theta given. Allowable shear stress, that means tau given. And G value is given. What do you need to figure out? Determine inside and outside diameter of the shaft. So at first you write down the length of the shaft with this mass. Then torque is given. So second data, you can say torque equal to this mass. kilonewton meter, then I convert in Newton meter, multiply by 1000. Okay, but this is given automatically. So we are getting on that I write down over here, right? Then angle of twist is given 2.5 degree, right? So angle of twist, or if say angle of deformation, whatever you mention, 2.5 degree. You convert in radian. How convert radian? 180 divided multiply by 180 divided by pi. So you got the radian. Theta. Then for that given, pick up the next one. It says shear stress should not be more than 90 megapascal. So that shear stress will be the maximum shear stress you can apply. So tau equal to 90 megapascal, converting them in Pascal. Next, you see shear modulus given 85. So you write down shear modulus of the shaft in this mass at megapascal. Now, you need to know what you need to figure out. It's saying figure out the inside and outside diameter. So if you figure out inside and outside diameter of the shaft, that I write. So how many unknown over here? You see we have two unknown. So obviously we need two equations to solve. So you see tau value given, you have one formula. You can say tau equal to torque into R divided by Z. You see torque given. R is not given. In that, what will be value of R? In that case, value of R will be what shear stress maximum at the outer fiber. So you can say D naught divided by 2, then
J.
by J, right? Then it says J. So you are getting one formula. And you know that J value. J will be, this is hollow. So J will be pi by 32 into D naught to the power 4. Then you say minus internal diameter di to the power 4. Is put the value. But di and d naught is not given. You need to figure out. So in the left side, right of her, you have the tau. You put the J value. Torque is given. You'll have d naught. So this equation have two terms. At the top, we'll have d naught. Then you have in the bottom, you have d naught to the power 4 minus di to the power 4. Second clue is given value of theta 2.5 degree equal to this mass radian. So theta, we know that theta equal to, right over here, T times L and by G times J. So this equal to T value is given 2.5, right? I can say 2.5 into 10 to the power 4 Newton meter. Then you multiply by L. L is given 3 meter, 0.3 divided by, and if you want, this program allow you to write like cosine. Okay. Then G is value given 85. So 8.5 into 10 to the power 10. This is our G. This one I can express in terms of cosine. Then into J, right? This J. So this J equal to pi by 32 star d naught to the power 4 minus d I to the power 4. Just twice. Okay. Then close. So what you see right over here in this formula, you can figure out that this value, because theta is already given equal to this mass radian. So you got d4 minus di to the power 4, right? And this mass is pi by 32. So in the bottom this formula, what will have? We have pi by 32 into d naught 0 to the power 4 minus d, I have to take out this one, minus d I to the power 4, right? Now you see in the bottom, you can figure out this value, because left side theta is given. This value you put it over here. This value you put it over here, then easily you are able to figure out the value of
D naught.
d naught. Then the d naught value you put it over here, you'll get di. Okay, very easy. So let's see. I have to delete this thing that I did over here. At first, this is tau, right? So I say tau equal to TR by Z. So this is my tau. This is torque R d naught by 2. This is my J. So you put all the value, we get this equation in terms of D. Then just 1 second. Okay, so we got D4 equal to this result. Now given theta equal to TL by GJ. So you put theta equal to radian, value of T, L, G, put it over here. And J equal to, I write down this one. So you get this value. Now this value, you put it over here. So you get D naught. After you calculate D naught, then you get DI from here. By using calculator, you can easily figure out. Since this value is smaller value, I convert in 0.14 meter. So better to convert in millimeter. So this is coming 146 millimeter, D naught, and DI equal to 125 millimeter. So, so far, any questions? How
No,
long
sir.
our class?
Sir, time is already finished.
Time already finished. Okay.
Yes, sir.
Any questions so far from here?
No, sir.
No, sir.
Right. Okay, I'll just take 2 minutes from you. 1 second.
Okay.
You draw the bending moment diagram, right? Now they have a one more term. It's called torque diagram. What is the torque diagram? You can figure out. Say, for example, you have a shaft, single shaft, and it has a different torque in different points. Right over here is a T1. Right over here is T2. Right over here, T3. Right over here, T4. And it has different points. Say I'm saying This point is the 4. This point is the 3. This point 2. And say this point is 1. So how will be a torque diagram? Torque diagram means kind of bending moment diagram. And right over here, summation of all torque has to be 0. T1, if you think clockwise positive, then you can say T1 plus, this is already anti-clockwise, then this is the minus T2. This is clockwise. I'm sorry, this is anti-clockwise, this one, T1, right? So anti-clockwise, I thought positive. And this one clockwise, T1, so I thought positive. But T2 rotating anti-clockwise, so negative. Again, T3, again rotating anti-clockwise, so this is minus. But T4, again rotating anti-clockwise, so T4 equal to 0. This is your one equation. Now, I told you that how we can figure out the torque diagram. So torque diagram kind of like bending moment diagram, but it will be different. Now, if I say figure out the shear stress in this shaft, it will not be figured out because you don't know which torque you will take. You will take the 1, 2, 3, or T4, or T3, or T2, or T4. You don't know. That seems like T3 might be look like the highest value, or might be not. So what we will do? You will think a x-axis. You start from point 1. See, this is point 1. This is point 1. For example, this is point 2, point 3. This is point 4. So you start from point 1. And I'm saying along this line is torque. Along this length of the shaft. So T1, what is our formula? Our formula in the free body, if it's rotate along this direction looking from this side, this is positive, right? Anti-clockwise, positive. So this one rotating clockwise. You can think that I'm taking clockwise positive, it doesn't matter. If you take clockwise positive at point 1, how much torque? T1. So this must, you got 1 point over here. Point 2, right over here, right? Then you come to the point 2. Point 2, you're getting opposite of this value, anti-clockwise, right? Say T1 500 and T2 200. Then right over here, you are still 500, right? I'm thinking clockwise positive, but this one anti-clockwise. So minus 200. So you're coming over here, minus 200, 500 minus 2. That will over here will be 300. So you say over here 500, then come to the right over here until you came over here. Still right over here is 300. Now you came in over here. This is clockwise, right? This 300 clockwise. Say this one, say for example 100. So this is rotating anti-clockwise, and this 300 is clockwise, right? Because this over here was 500 minus 200 or anti-clockwise. Still, this 300 anti-clockwise. I'm sorry, clockwise. But this 100 again anti-clockwise. So right over here again subtract 100. Then coming over here, this will be 200. And right over here, then it has, this one has to be 100. This is anti-clockwise. So this 200, I'm sorry, this one has to be 200. This 200 and 200, 0, double line. Okay. So you see that what is the maximum torque? Which area is critical? You see, this region has maximum torque. That amount of torque is 500. So this kind of diagram is called torque diagram. Sometimes you need it to know which point is the most critical and carrying the highest load. So in the next class, we will solve problem with torque diagram. Okay. So any questions so far? I think you're all